Well, hello, Science 10s. We are going to continue on with mechanical energy. So we learned the formula last video. Potential plus kinetic is equal to mechanical. And now we're going to so we did a couple practice problems in the last video. Now we're going to talk a little bit about the law of conservation of energy. So this is a physics principle. And in a lot of cases, we can understand that the potential energy of an object is going to be converted entirely into kinetic energy. Now, we already know that there's always some loss of energy. We always know that no energy conversion is ever 100% efficient. We learned about this way long time ago in the law of conservation of energy. We learned about thermodynamics, and we said there's always energy transformations, one energy being transformed or changed into another, and no energy conversion is ever 100% efficient. But in saying that, we're now going to pretend that they are. We're going to pretend that there is no loss of energy in the form of heat or friction, and that if we know the potential energy of an object, then it will be entirely converted into kinetic. Okay, so let me show you an example, and this will help to make it clear. So here's this problem where we've got a rock. So here's me with my little rock, and I know the mass of my rock in my hand, and I'm dropping it. Okay, so right now, the potential energy that it has is due to the mass times the gravity times the height. At this point in time, this rock is not moving. I haven't dropped it yet, so the kinetic energy is zero. So I'm about to drop this. It's going to drop into the water. So I know the height, 30 meters above the surface of the lake. I know the mass of the rock. It's 1.5 kilograms. 3 sig there, 3 sig there. I always know gravity. We are on Earth. Gravity is 9.81 meters per second squared. So that's in your data booklet. G is the acceleration due to gravity. So I know the potential energy, of this rock, this object that it has when I'm holding it before I have dropped it. So we're going to assume that the potential energy of this rock, the stored energy because of its position, it's above the ground by 30 meters, is going to be entirely converted into kinetic energy. So it went from zero kinetic to it's now all kinetic. And when it hits the water, it is on the bottom. So there's no more potential energy, right? There's no more height. So that potential energy at the top is going to be completely converted into kinetic energy that the rock has at the bottom once it just about touches the water in the lake. So potential energy at the top will be converted into the kinetic energy at the bottom. Okay, so this is an energy conversion. And again, we are assuming that we're not losing any energy due to our friction or heat or anything like that. So EP at the top is being entirely converted into kinetic energy of this object at the bottom. So what is potential energy? Well, potential energy, mgh. What is kinetic energy? You know this as well, 1/2 mv squared. I am looking for the speed of the rock just before it strikes the surface of the lake. So I need to calculate speed, not speed squared, but speed. Let's see how we're going to do this. Let's isolate v, get it all by itself. Let's divide out 1/2 times the mass. I'm going to do the same to this side, 1/2 times the mass. So the 1/2 cancels off both sides. The mass cancels out here, leaving v squared. Now look at this, guys. Mass on top, mass on bottom. It cancels. It's gone. Mass is gone. So even though they've given us the mass of the object, we don't even need it for this calculation. Remember, we can write this as GH over a half, or another way of writing this is the same as 1 times mgh over a half. 1 divided by a half is 2. So 2gh is equal to v squared. So again, I'm looking for the speed of the rock, not the speed squared, but the speed. So I have to go from v squared and find v, and to do that, I need to take the square root of both sides of this equation. So the root of 2 times the gravity, which we know is 9.81 meters per second squared, times the height of the object. Oh, there's an error here. This should read 30.0 meters, right? That's 3 sig digs. That's going to affect your final answer if you don't write your sig digs. So the root of 2gh is equal to, well, what's the root of v squared is v. So you plug in these values onto your calculator. So that took a while, but we've got our formula written out, right? Potential at the top is equal to kinetic at the bottom, and then start substituting in and rearranging to solve for the speed of the rock, v. Substitute in your values, so 2 times 9.81 meters per second squared times 30.0 meters. So what happens here? Meters times meters is meters squared divided by seconds squared. Now remember, we're taking the square root of that. So the square root of a meters squared per second squared, it's meters per second. So there's our speed. The speed is going to be 24.3 meters per second just before that rock is going to hit the surface. Okay, so again, showing your work. Final answer, correct sig digs, 3 sig digs, units for speed, meters per second, rounding, scientific notation, and remember, I made an error here. It should be 3 sig digs, not 2. Okay, so now we are going to be talking about a pendulum. And a pendulum, you guys have all seen a pendulum, right? Like in a grandfather clock, or you've all seen what a pendulum looks like. And so a pendulum is like a little bob or a little something, a little round thing, usually on a string. And remember that when we talk about our mechanical energy, EM is equal to EP plus EK. Mechanical is potential plus kinetic added up together. And so we could calculate any of these things in the equation. Now, when the pendulum is at the very top, before you let it go, the mechanical energy is all potential. It's not moving, so kinetic is 0, so this is 0. That means that the mechanical is equal to the potential, right? It is above the ground by a certain height, right? So that's stored energy. It has a certain height in meters above the ground. And that's how we find mass of the little bob or the little pendulum. We would know. We know gravity, 9.81 meters per second squared, and we'd be given the height. Now, as soon as that little pendulum starts to move, it is losing height. So the height is going down. So that means potential energy is going down because it's losing height. But it's starting to pick up speed. Since the speed is going up, it is going to be gaining kinetic energy. So what's interesting here is that the mechanical energy is the same all the way through. So let's say here the mechanical energy is, let's say it's 10 joules. And so potential energy would have to be 10 joules because there is no movement. Object, the pendulum, the little bob is not moving. So potential is equal to mechanical. As the object starts moving, the potential starts to go down. Let's say maybe it's now 5 joules. Well, we just said that the mechanical is not changing. It's still 10 joules. So what do you suppose the kinetic is? Well, kinetic was 0 up here. It wasn't moving at all. And now, because it's in motion, the speed's going up, it's going to have some kinetic energy, and the kinetic energy has gone up. Okay, so 5 and 5 is still 10. Once we get down to the midpoint, or like the bottom of the arc of the pendulum, or the little bob gets down to the bottom, the speed is at its maximum now. So EP plus EK is equal to the mechanical energy. So again, mechanical energy is not changing. It's going to be the same value all the way across. This object has now no height above the ground, right? It's now at a height of 0. So that means that MGH, with H being 0, this is a value of 0. So all of this energy is now in kinetic energy. And this is the fastest speed. The speed is the highest. The speed is at its maximum at this point in time. And that means that for our 1/2 mv squared, for our EK, we're going to have the highest speed. That's our maximum kinetic energy. So in other words, at the bottom, the mechanical is all kinetic. There is no potential energy because it's not above the ground anymore. It's no gravitational. It's not got any stored energy due to gravity. And so then let's say that this little pendulum is going back up to the other side. Well, what's happening here is now it's starting to slow down. The kinetic energy is slowing down, but it's going back up in height. It's halfway to where it was. So the same deal is that the mechanical is still going to be the same value, still 10 joules. And kinetic, it's gone down from its maximum. Let's say it's now at 5 joules. And we're not at 0 potential energy anymore. It's gone up because it's halfway up. It's like a height of whatever halfway is. And so you can see that the mechanical is kinetic and potential. And then again, once we get to the very top at the other side, and again, we're assuming that there's no energy in this conversion lost to heat or friction or anything like that. The mechanical is all potential. The object is not moving anymore here. Kinetic is 0. Okay, so